Okay, thanks, Allie, and thank you everyone for joining. I'm excited to have this opportunity to speak with you today. I'm gonna get situated here. Okay, hopefully you can see the presentation. I'm seeing a nod. Okay, good. So my name is Matthew Vaughan. Like Ali said, I work for the Lake Champlain Basin program. And today I'm going to be going over kind of an overview of what we've been working on for agricultural water quality in Vermont specifically. So I wanted to start just pretty big picture, thinking about what the Basin program does in general. So many of you have probably worked with us in some capacity before. We have a very wide-reaching mission, which is to coordinate and fund efforts that benefit the Lake Champlain Basin's water quality, fisheries, wetlands, wildlife, recreation, and cultural resources. So we're really only talking about a sliver of that today. And a lot of what we do for agriculture specifically is really focused on phosphorus. And this is probably not news to many of you. This graphic is from our 2018 State of the Lake and Ecosystems Indicator report. We have a new one coming out next year, so keep your eyes peeled for that. But in that report, we showed some of the modeling done for the 2016 TMDL for phosphorus in Lake Champlain, which showed, hopefully you can see my cursor here, that 38% of the phosphorus load to the lake is due to agricultural contributions in the entire Lake Champlain Basin. That includes Quebec, New York, and Vermont, of course. But only 18% of the basin is covered by agricultural land. So you can see, there's kind of a breakdown of per land area, how much agricultural is contributing. For phosphorus, it is less than developed lands, but more than forest or wetlands, for example. So we have a lot of work to do to reduce phosphorus on a large scale in the basin. For Vermont agricultural land specifically, this modeling showed that the base load from 2001 to 2010 was about 261 metric tons per year, or 41% of the load from Vermont as a whole. And the TMDL establishes a target to get that down to 118 metric tons per year, which is a 55% decrease. So that's not small peanuts. That's a lot of work to do. And that's, again, why we're focusing in on phosphorus for agricultural water quality. I also just wanted to say a few things about how we work. We have a document called Opportunities for Action, which is our management plan, and it's kind of an adaptive management model. And in this was revised in 2017 and signed by environmental leaders from the 3 jurisdictions we work with. And it identifies strategies like researching ways to improve BMP performance, providing technical assistance for farmers, optimizing fertilizer applications to reduce nutrient load through research and direct farmer support, helping farmers meet clean water regulations through cost-sharing programs, and supporting sustainable ag practices that address these water quality concerns, and also to support phosphorus removal from tile drains and ag ditches. And we'll be talking a lot about that as I go forward in the presentation. So all of the work you're seeing goes through our active volunteer committees. The Technical Advisory Committee is a group of 25 or so scientists that get together once a month and talk about these issues and help direct the research and implementation of the Lake Champlain Basin Program. And on a higher level, we have a Lake Champlain Steering Committee that awards our grants and helps us identify which partners we're going to work with and what we're going to be focusing on. So again, for the talk today, I'm going to highlight some of our recent work and ongoing work and try to highlight the most important takeaways for you to leave with. And I also want to say that my background is really in water quality and hydrology. I'm not really an ag person. So if the hard questions come, I may just have to get back to you with answers on those. But I've had to become more of a generalist in this position, which is really fun. So I think we're going to start. Yep. Okay, we're going to talk about tile drains. So you all probably know more about tile drains than I do. This is something we've focused on a lot in the past few years because it's something that's changing very quickly. The tile drainage is changing really quickly in our basin. We don't have a good handle on how this is impacting the hydrology of the basin and water quality for the lake. So of course, farmers appreciate the benefits of tile drains, like better growing conditions, improved soil structure, the ability to get onto their fields earlier and more frequently to do the work, which allows for more timely planting and harvesting of their crops. And of course, because it's able to lower the water table, it can improve crop yields, and for all the reasons I already mentioned. And phosphorus loads from tiles used to be considered pretty much negligible, but we now understand that they are potentially a significant source of phosphorus. And of course, they influence hydrology alongside with phosphorus loading for obvious reasons. You're draining the fields in ways that wouldn't be drained otherwise. So, so this is something we, like I said, we've been focusing on, and especially because the extent of tile drainage in the basin is not really known. The best estimate I've seen for tile drainage of Vermont cropland is about 5%, although this can be as high as an estimated 70% in some sub-watersheds. And of the reported tile drains across Vermont, about 80% of them are associated with dairy production. So for our work that we've kind of been attacking this from all sides here. We started with a literature review, and then we began a few different monitoring campaigns to see what is actually coming out of these tiles, and that work is ongoing. We also funded 2 filter experiments to see if we can remove phosphorus at the end of these tiles. And we've also funded some modeling to see whether we can identify some best practices to again, minimize the amount of phosphorus loss from fields through tile drains. So I'm going to start with the literature review, which is always a good place to start to see what else is out there. And it turns out a lot of people have studied tile drains all over the country and in many places in the world. This work was done by Stone Environmental, and Julie Moore led this project just before she became the Secretary of Vermont A&R at Stone. So they found 166 references, almost all of them peer-reviewed, and they came up with some really important takeaways for the hydrology and phosphorus concentrations and loads. So just some of these takeaways: hydrology, for the hydrology changes with tile drains, they found that the total annual water output often increased by a factor of about 2. So we're seeing more water off the field and sooner rather than a field that's not tile drained, which is not a surprise. It's kind of the entire point of tiles is to get water off the field. We saw a reduction in surface runoff. Again, that's the point, not a surprise. Lower water tables, that's the benefit. That's why farmers are doing this. Eliminated saturated areas, of course, and it provided more capacity for infiltration during rain events. And we've learned that most water, about 50 to 90%, is delivered through tile drain flow. And that can contribute in a majority of stream flow in some smaller or headwater watersheds. So this is a really important component of the load of water and nutrients to especially these smaller watersheds if you have a lot of tile drainage. For phosphorus concentrations, they found that in studies around the country, it's really highly variable over time and across space. And most studies found that phosphorus concentration was proportional to the tile flow, where more flow meant higher concentrations. And we'll come back to that later. So remember that one, that it's proportional with flow. And we also found that seasonal patterns existed somewhere, but not others. And when they were found, they weren't exactly consistent with each other. So sometimes you see seasonal patterns, sometimes you don't. And sometimes they're all different. So there's no rhyme or reason there with all these studies. And phosphorus loads were similar in magnitude to surface runoff loads. And one of the biggest takeaways is that they can include significant components of both dissolved and particulate forms in the phosphorus load. So it used to be thought that you wouldn't be getting really any particulate load in the tile drains because it's subsurface. You'd only be getting that percolated water. But in fact, when you have preferential flow paths in soil cracks and macropores, and also depending on the age of the system and the condition of the tile itself, you can get quite a bit of that particulate phosphorus making its way into the tile system. So this is this and everything else I'm going to be talking about, unless it's kind of ongoing work, is all available on the Lake Champlain Basin Program website. This is an excellent resource for everyone if you want to dig deeper. And the Vermont Agency of Ag used this literature review to develop the 2018 Required Agricultural Practices Rule Amendment to include requirements like barnyard and feedlot placement that can't be sited over tile drains anymore. New treatment areas for ag waste cannot be within 200 feet upslope of a tile drain. Rodent guards are now required on the ends of new tile drains, and surface inlets are now no longer allowed on or near cropland, which is a big change, again, based on the findings of this literature review. So once we had all of those findings of work from other people, we took the next step to actually monitor tile drains in the Lake Champlain Basin. That's something, you know, anyone who works with farmers knows that it's hard to convince them of you know, people who work with the land that anything is applicable unless it's studied here, which is for a good reason. You know, we want to see what's going on with our watershed right here in the Lake Champlain Basin. So we did that. We monitored 12 sites in Jewett Brook watershed for the first year of this. And then the second phase, we reduced that to 5 in Jewett Brook and then added some in Addison and Rutland counties. And the way this worked is, this is again, was with in partnership with Stone Environmental. And the way they designed these experiments was to intercept the tile. They dug a big hole. They intercepted the tile and put in this type of magnetic flow meter here to measure the tile discharge moving through the pipe. And then they had auto samplers take a consistent amount of sample volume that was tied to the flow itself. So in that way, they could come up with a flow-weighted mean concentration that was mixed into a large carboy. And then that way we could get a really accurate measurement of the phosphorus load over time. And we also looked at total phosphorus, total dissolved phosphorus, total nitrogen, and total suspended solids, and of course, water flux itself. So there are a lot of important takeaways from this phase 1, again, focused on Jewett Brook. Because we only had 12 sites, it was kind of a low sample size to make statistically significant conclusions about what type of site might have yielded certain results. But we did see some interesting patterns that we're able to report on. First of all, we saw that phosphorus concentrations and aerial loads, so load per area, were higher in row crop fields compared to hay fields. That was a big takeaway from the study. And not surprisingly, total phosphorus and total dissolved phosphorus concentrations were higher from fields that had received manure compared to those that didn't. Again, not a big surprise there. And again, maybe not a surprise, when manure application coincided with wet weather, especially, we saw very high phosphorus concentrations. And that's, you can see some of those reflected here. 6.9 milligrams per liter is exceptionally high for phosphorus concentration. So beyond those, some important takeaways I want to discuss. Although annual tile discharge, the amount of water, was correlated and positively correlated with field size, phosphorus concentrations did not vary significantly with field size or discharge. So thinking back to what we saw in the literature review, in most other studies, that was a relationship that folks saw. Here in the basin, we did not see that. And phosphorus concentrations and load did not seem to vary with soil characteristics or with the presence of cover crops on corn, which is a bit of a surprise, but again, low sample size. So those types of things are hard to see with just 12 sites. Similar to other areas, we did not see any obvious seasonal patterns for the proportion of total phosphorus that was made up with dissolved versus particulate forms. And the flows out of these tiles range from 0 when they were dry to over 3,000 liters per minute, which is a pretty incredible flow at the end of a pipe. The loads to Jewett Brook could be estimated just by taking the loads from the fields that we were monitoring and kind of extrapolating that to the entire watershed and then looking at what is measured at the long-term monitoring site at the mouth of Jewett Brook to try to get an idea of how much of the total phosphorus making its way to St. Albans Bay through Jewett Brook is coming from the end of a pipe in tile drain fields. And the best estimates for those we came up with were 806 kilograms per year of total phosphorus and 355 kilograms per year of total dissolved phosphorus, which represents 26% for TP and 16% for total dissolved phosphorus. And that was kind of our best estimate with quite a bit of uncertainty on either end of that. And so with reasonable confidence intervals, that estimate could be as high as 45% for TP and 29% for TDP. So that is, whether it's a quarter or nearly a half of the total phosphorus load coming from tile drains in Jewett Brook. I would call that a significant amount, but it really depends on how you look at it. It seems like a lot, and especially it's something we can address because we know where the ends of the pipes are, and it's kind of like a point source in that way. It is, maybe only a quarter of a load, and there's bigger fish to fry in other areas. So it really depends on your point of view there. And the third takeaway I wanted to mention was that on average, about half of the total phosphorus was in the dissolved form. And again, we measured TDP, total dissolved phosphorus, and that proportion varied among the monitored tile systems. It ranged from about 30% in fields with fine textured soils and was up to about 75% for fields with long-term no-till practice. And that's possibly because the long-term no-till practice can create some macropores and some preferential flow. So the takeaway there is that, again, particulate phosphorus can represent a surprisingly large fraction of the total phosphorus in tile drained water.
So Matt, there is a question from Karen with DEC. He was asking, are the Jewett watershed soils mostly clay?
I'd have to go back and look to remember how many of them are clay. I think there's only a few of them are predominantly clay, and that's one of the reasons that in phase 2 of this project, we wanted to move to Addison County, where there was a higher prevalence of clay soils to get a better representation of that type of field. Does that answer the question? I'll take that as a yes. I can only see you, Ellie. So, all right. So I apologize for the background noise. I have a toddler and a 13-month-old, so in a small house, but we'll do our best here. So the next thing I'll talk about is an experiment to actually filter out or chemically absorb phosphorus at the end of a tile drain. And the analogy that we've kind of been using is, you can think about this as a technology like a septic system, in that it's something that's on site. We could develop a best practice for it if it's cheap and accessible and it's not a complex design. This is something that could be implemented throughout the basin and throughout the region as a way to capture phosphorus before it enters our receiving water bodies. So what you're seeing here is the installation of a tile filter. Again, this is in partnership with Stone Environmental. And the design here, actually, so I'll start by talking about a benchtop experiment. So this is, we looked at three different mixes of media to determine what would go into the actual installation. So one was just half-inch pea gravel, which is kind of a control. We had pea gravel with 5% activated alumina, which is a highly, it's a substrate with a lot of surface area and good absorptive capacity. And then the third one was crushed St. George Black, which is a shale material that is pretty widely available in the region. And the way this worked was they had water spiked with phosphorus, and they continuously added phosphorus to maintain a constant concentration. So they're able to measure what was added, and they could conclude that whatever was added to maintain a concentration was absorbed by the media. So that's kind of the thinking with this experiment, to see how well these media would perform if installed into a field. And so here you see just the pea gravel control, the activated alumina mix, and then the St. George Black and blue. And so you're seeing the addition. So this is really what was absorbed by the media. And the activated alumina and the St. George Black really performed very well. The pea gravel absorbed a bit and then kind of petered off toward the end of the experiment. But it's not really a surprise that St. George Black and this activated alumina absorb phosphorus. We knew that already. It's really kind of a balance or a trade-off of hydraulic conductivity and filter clogging. You want to avoid clogging the filter along with this absorptive capacity. So this gave us some confidence that if we use activated alumina and or St. George Black, then it would be probably a good filter, at least to start with, for this experiment. And here's a schematic of these filters, and this is not exactly how it would look if it were implemented on a large scale, or if this became a BMP. This is a setup to study the filter. So you have inflow from tile going here. Allie, you can see my mouse, correct? Okay, thank you. You have inflow from the tile here, and then you have a monitoring well here where we can take water quality and quantity samples. And then it splits into the two filters. And these each are 5 feet wide, 65 feet long, with 2 feet of media backfilled with native soil. They're lined with 10 millimeter thick heavy duty plastic. And the pipes are 6-inch perforated. The field it's draining is 94 acres, and its design flow is 6 liters per second per filter for a total of 12 liters per second, which is about, the flow is kind of the average, or the median of what we saw for this tile during the first phase of monitoring. And for the experiment, we went with 2 different filters, filter media. One was St. George Black, and the other was a mixture of St. George Black and that activated alumina that we talked about. And so the residence time through here is designed at about 50 minutes. And you can see these arrows. The water will be split into these two lines of pipes, and then slowly percolate across to the outflow, which is in this other on the other side here, and then into the outflow sampling well for both filter. So we have the inflow monitoring here and outflow monitoring here on the 2 filters. And we had some delays with this project for several reasons, but we're getting some good data from this, and we're hoping to have some results mid next field season, I think it is. So
there's a question, Matt.
Sure.
Why wasn't drinking water treatment residuals chosen as a media for phosphorus removal?
That's a good question. I know that's been a contender for these types of filters, and I can't recall off the top of my head why it wasn't used in this experiment. I know there's a reason, but it's escaping me at the moment. So I'll have to dodge that one for now, and maybe it'll come to me by the end of the talk, and maybe Allie, you'll have to let me know who asked that, and I can get back to them.
It was Karen Bates, and Angie Allen actually put a resource in the chat that may get at that question as well.
Okay, thanks. And maybe others can confirm this. I think it might have to do with hydraulic conductivity, which has been an issue with these filters before. The first round of these in the area done by the same team, which is part of the strength of their proposal here, was that they've done this filter before and it clogged quite quickly. So there's a few things in this design that are aimed at reducing the clogging with those fine sediments, because if you don't have hydraulic conductivity, you're not going to get that water moving through to get any absorption. So I think that's why, but again, it's escaping me at the moment. So it's certainly true that treatment residuals will absorb phosphorus. So and there's a lot of materials out there that do. Again, it's that trade-off of getting the conductivity and the absorptive capacity over time, and of course, cost and availability and all these things. So. So Karen, I'll follow up with you. All right, good to move on, Allie? Okay, thanks. We have a second tile drain removal experiment. This one is also using St. George Black shale, not a mix, just the shale alone. This one's a bit different. It's designed specifically for base flow and tile drains. And this one it's kind of it's a neat, simple design where you have a ditch here and a tile drain going into a well with a pump. And that pump will bring it up into this cell that you see here, and it'll kind of upfill through that cell and then out the top. So the contact time is kind of moving up through that filter system. And again, it's taking sample on a flow-based in a flow-based way, so we can get some good load estimates from this experiment. And this one also has had some delays for multiple reasons, and we have about half of a field season under our belts here, and then we're going to probably continue this into the spring, because even though it's designed for base flow, we've been having a hard time getting the flow to sample in the field that was chosen for this site. So I'm sure you're all familiar with field work woes, and that's not uncommon for this type of work. So, but I think we're going to get some really good results from this one. We've already seen some reductions in total dissolved phosphorus from this style of filter. Okay, and the next, I think this is the last tile drain project I'll talk about. And so we did the lit review, we've done the field studies, we've done the filter experiments. We also funded a study to model field management practices for tile drain fields. And so a team, it was a group called Nutrient, which is has an interest in promoting sustainable practices for dairy farmers, and Stone Environmental, the modeling team at Stone Environmental, worked on this together to calibrate an APEX model, which stands for, I always struggle with this one, Agricultural Policy Environmental Extender, I think it is, which is a field-based model that can simulate hydrology, nutrients, pesticides, and help you manage a farm on the farm scale. So they were looking at BMPs like manure injection, no-till, cover crop, a combination of cover crop and no-till, and then some more innovative technologies like dissolved air flotation, which was new to me when we started this project. It's a process where you use chemical inputs to aggregate small colloidal suspended solids into larger flocks for separation and dewatering, and then you can put those in a stackable pile and export them or move them around the farm for a more targeted application. There's also evaporation, which is a bit more simple. It's where you separate it into manure into solid and water components that are heated, sterilized, and distilled. And then you get a coarse fiber product, a dry solid manure product, liquid ammonia, and then relatively clean water from that. And again, the idea is you're separating out these components and you can have a more targeted approach in time and space, or even export these materials and sell them in theory. So what I'm showing here is the calibration of the APEX model with the tile drain monitoring data that we collected. We actually use that data in this model to then try to simulate what benefits we get with our best management practices. So this included several of our tiles at Jewett Brook and some tile drain monitoring done in New York at the Minor Institute. So this was a basin-wide study. So I'll just jump right to the fun part, the results. So these are the more conventional best management practices, and you're seeing different components of the phosphorus load, tile phosphorus, soluble surface, and sediment surface, and then the total phosphorus, in this case, the reduction in losses from these different practices. So in general, the combination of cover crop, no-till wins out here with the total reduction, and we're looking at optimal phosphorus scenarios, and we're going to look at higher phosphorus soils in the next slide. But we're looking at about a bit over 30% reductions with this combination in tile drained fields. And manure injection, surprisingly, you don't get any reduction in the tile drain fields there. And then this is the same thing, but for high P soils. So we're starting from a higher point. and you see a bit less than 30% reduction. It's a bit harder to drop with these best management practices with tile drain fields. Oops. And then we can look at the more innovative manure management practices with the dissolved air flotation and evaporation. We see with optimal pea soils about a 5% reduction in the total phosphorus loss, according to the model simulations. And when you have high pea soils, that's when you really start to see the benefits of these more innovative technologies, and about 15% reduction with these two for total phosphorus reduction there. Okay, if there aren't questions on that one, just check time here. Okay. We're 10 after, Alex. Should I try to breeze through to the end, or what do you think? Maybe about 5 more minutes, or?
I'd say keep going. Yeah.
Okay, cool. All right. So next, many of you may have heard of Farm Prep, which stands for Farm Pea Reduction Planner. And this is a really neat online tool that the Basin program funded. This is, again, with the modeling team at Stone Environmental. And so this is a tool that helps farm management planners quantify reductions in farm scale pea losses, and also on a bigger scale, meet sub-watershed TMDL goals through field level practices. Because the TMDL lays out what each sub-watershed needs to achieve, but doesn't say how a farm or what a farmer needs to do to get there to do their part. So this is an optimization tool where a planner can go in, draw their fields right on an online tool, and then the tool will in the background grab all the publicly available data about the soils, the slope, and everything else that it might have available. The farmer can then enter in field management practices that are the baseline conditions, and the tool will run thousands of scenarios to identify the best combinations of best management practices that will achieve maximum phosphorus reductions, and then ones that might not be the maximum reductions, but might be more palatable to a farmer who actually has to do the work. So this has had 2 phases. The first was to pilot it in St. Albans Bay watershed, which I think was received really well. And the second phase was to expand it for the entire Vermont portion of the Lake Champlain Basin. And during that expansion of the tool, we held several stakeholder engagement meetings where we got a lot of good feedback. So the Stone team added many more crop rotations and crop types. They added more spring and fall tillage combinations. I think I show, right, they added a second growing season, a short season and a long season for Vermont. They added the ability to overwrite the information that it's automatically grabbing. So if you have better data on your soil than what it's grabbing from the Sergo database, you can just enter that right in. And then you can also add tile drainage information, which will affect how the model handles the phosphorus reductions based on our understanding of how tile drains work. A few more improvements. Farmers and their managers can exclude or prioritize best management practices that they are really interested in trying or not at all interested in trying. This way it won't give you back a bunch of results that you have no interest in implementing, which makes a lot of sense practically. And then you can also, originally, like I said, you can draw on your fields in this tool, but the improvement allows you to upload a shapefile if you happen to have GIS information about your farm. You can just upload that right into the tool. So this is currently being used. It's available online, and it's hosted through Basin Program support through the end of 2022 at this point. And I think it's going to continue well beyond that, because I think folks are finding it very useful to actually come up with solutions that people can use on their farms. So I think I have a few more studies. Did you have something, Allie?
Yeah, there's a question from Katie with DEC. Do you have a file or report outlining the phosphorus reduction efficiencies applied for the various BMPs?
Yes, that will all be in the it'll all be in the final report for this project, which is available on our website. And I think it's in the documentation of the tool. Also, if you go to the Farm Prep tool website, And those all come from the Vermont Agency of Ag water quality expert panel that got together and determined the reduction efficiencies for all BMPs in Vermont using all the available literature and monitoring that we've done in the area to the best of our ability. So it's a good question. Okay, I'll just kind of breeze through a few more here. This is an ongoing project to look at whole farm nutrient management. This is with UVM Extension, and Heather Darby's leading this one. It's a really important idea, I think. You know, traditional nutrient management plans really, I think, look at what's applied on the field and what's required for the soil for plant uptake. This whole farm nutrient balance idea dives a lot deeper at the whole farm, you know, what's coming in to the bubble of the farm and what's going out in every different direction. So it's going to look at feed, animal feed, phosphorus levels, fecal phosphorus for the animals, herd health, and what's required from the animals, for the animals, I guess, soil health, soil test nutrient levels, financial statements to try and save the farmer money. So they don't have to buy, you know, bring in more nutrients than they need. That will then make their way to the waterways, and then milk quality and quantity for dairy farms. So the results they'll be used to promote adoption of this idea potentially throughout the entire basin. And I have more to talk about, Elliot. I don't want to step on the Q&A period. Should I keep going? All right, sounds good.
I think 5 more minutes would be good.
Okay, cool. So this is a study that was a pretty long-term one to look at edge of field results for best management practices. This again was in partnership with Stone Environmental. They've clearly done a lot of our agricultural work in the basin with basin program funds. So this was a paired watershed study to look at the efficacy of a grassed waterway to reduce sediment, phosphorus, and nitrogen loads. And it ran from October 2015 to April 2019. And I'm just going to skip to the results here. So again, there was a kind of a calibration period where there was control and no treatment, and then the treatment period. And there were a lot of limitations to the study because of several confounding factors and difficulties, but I'm going to go with the results first, and then I'll mention those. So we monitored 51 runoff events through the control period and 41 post the construction of the grassed waterway. And one of the things we found was that event flow was significantly higher with the grassed waterway. So we're getting more water, probably because things could run off more easily without the vegetation, the crops there slowing them down a bit. So the good news is phosphorus, nitrogen, and total suspended solids concentrations were lower in the treatment period following grass water construction. And when we eliminated that initial treatment period when it was installed but not really cooking and it wasn't like grown in, when we took out that early period, that difference was even stronger. However, because what I mentioned about the event flow being higher, that somewhat canceled out our effect of the concentrations being lower, and phosphorus loads had no change, even though the concentrations were lower, and nitrogen loads were even higher actually than before the construction. Total suspended solid loads, however, were lower, and that's one of the main goals of a grassed waterway, is to reduce erosion. So we did achieve that goal of the grassed waterway. So this study, like I said, was really complicated. There were ownership changes to the farm. There was no crop planted on either study watershed in 2018. There was no tillage or manure application during the final field season like there were supposed to be. And these probably impacted our ability to see the benefits of a grassed waterway, if there are stronger benefits than what we observed. So this definitely was a learning process for us and showed us that paired watershed studies are really hard to pull off. So keep that in mind if you're ever thinking about doing one. Confounding factors, yes. Okay. So I just wanted to quickly mention some of the other work, and I'll glaze over these, but other work to implement some of these these and other practices that the Basin program has supported recently. So we've supported innovative roller crimper technology for cover crop termination. We've supported targeted implementation for critical source areas that were identified in the Missisquoi Bay watershed. You all are probably familiar with the multi-partner practice tracking database that's geospatially explicit and helps people work together. And that was a long process getting off the ground, but I think it's a helpful tool at this point. We've worked with the Farmers Watershed Alliance to implement conservation practices in their area. We funded several years of the ACAP program through UVM Extension, and we supported a pretty neat training program for engineering capacity for dairy farms run through Cornell University Extension. We also have several videos on our website that are meant to communicate some of these innovative practices to farmers and to other people who might be interested in what farmers are doing to improve water quality. These are all available. It's under Clean Water Commitment on our website. And I encourage you to check these videos out if you have a few minutes. There's other really neat projects going on that you may be interested in. They're not specifically agricultural, but they do tie in because of floodplain and wetland protection and conservation. So we have a study looking at the potential for our floodplains throughout the basin to be restored. And if we were to restore them, how much phosphorus reduction would we get? And there's a really cool field study going on to really try and quantify that and put a finer point on it. Similarly for wetlands, if we can restore wetlands, how much phosphorus reduction benefit would we get? And this is really looking at soil incubations and how phosphorus is moving and transforming through the system. There's a really cool modeling component of this project. And finally, you may have heard about the treatment train idea on Jewett Brook. And this would be to actually divert some water from Jewett Brook and treat it outside of the stream to try to remove physically and or chemically phosphorus before it enters St. Albans Bay. So currently we're in the technical feasibility phase where we're looking at modeling some of these ideas, seeing if it would be technically feasible to do this work. And I'll also put a plug for a LCBP science blog that is coming soon. And the idea here is to do kind of what I'm doing today to try to give high-level takeaways. We have a lot of research and work going on, and we think we can do a better job at getting it out to you. So the audience here is really all of you who's already doing this work. You're working on water quality in the Lake Champlain Basin, and we want you to kind of be able to learn and internalize these takeaway points and incorporate them into your work. So the idea here is they're going to be very short articles, maybe take 4 or 5 minutes to read with, we call them too long didn't read points at the top, which I guess is something the kids are saying these days. And that way, you can have easy access to our research results. And then of course it will link to the 150-page report that you can read if you want to, but that's hard to digest. So we want to make it more accessible to everyone. And I think that is all I have for a presentation. So
thank you so much.
right,
So let's open it up to questions. If folks want to unmute and go ahead and ask their own questions, that's fine, or you can type it into the chat and I'll mention it when it comes up.
Hey there, this is Heather Fenberg from Watershed Management. One of the questions I had was in regard to the tile drains where you're using basically an alum treatment or activated aluminum. And I guess my concern there is, I'm not sure how deep some of the tile drains are, but if the pH drops low enough, then that could basically convert that aluminum to the toxic form. So the pHs may be, plenty high, but I was just wondering if that was looked at with some of this treatment.
Yeah, thanks for that question, Heather. That is so. Alum, as I think you said alum. So alum is a term that's usually, I think, used to describe aluminum sulfate or aluminum salts, and those are generally used in open water application to try to precipitate out phosphorus and remove it from the water column. What we're using in our tile filters is aluminum hydroxides that have been dehydroxylated. So it's really a solid product. And so the idea is it's a very high surface area, solid substrate that can absorb a lot of phosphorus. And then once it's absorbed that phosphorus and reached its adsorptive capacity, it's physically removed from the filter. So I don't want to minimize your concern that alum can potentially have that effect in some open water systems. In the tile drain filters we're talking about, it's a different compound, a different material.
Any other questions for Matt? Okay, well, thank you so much, Matt, for this presentation. I see your email there. If folks have questions, they can follow up. And this, again, is a friendly reminder. This is going to be recorded. We're putting it on our SharePoint. I'll try to get the resource that was put in the chat and put that in the file as well. So reach out to me if you're not on our clean water, on our partnership listserv, or don't have access to SharePoint and that's something you're interested in. I can help you get on both of those things. And I just wanted to send a reminder as well that the next webinar coming up is on Wednesday, November 4th from 12:01, and we will be joined by Jim Eikenberry, Chris Smith, and Ryan Crean to talk about wetlands work in Vermont, success stories, what they're focusing on right now, and collective messaging that we can have as folks are interacting with landowners in the field. So thank you all so much. Enjoy the rest of your day.